this recording, we will be going over an example again, Amitrack dataset, and we will look at how smoothing techniques apply on this dataset. So the first thing we do is just downloading the data set. We have the libraries first. I have the dataset, Amitrack data. Then I have changed the Amitrack dataset to time series. Then we plot the time series, and we see that we have a trend and we do have a seasonal. So we have seasonalities and we have a trend. So in this case, to use a smoothing technique, simple exponential smoothing, we have to make it level. So we have to remove the trend and we have to remove the seasonal, right? So to do that, we're going first to do the simple exponential smoothing. First, we are going to bolt the difference series. We are going to remove the seasonality and the trend. So to do that, I'm going to create a new data, lag data. And I did this last time, how to remove the trend and seasonal. So we're going to create lag 1 and lag 12 months. So ridership minus lag ridership 1. Also, we're going to do difference 12. After that, we're going to difference twice. So after differencing the 12, we're going to difference it once. I should have muted. I'm adding these guys. Okay, here we go. Muted difference ridership. Let me do that just to see what's a mistake. An argument difference equal lag. Here you have an issue of spelling. Okay, ridership. So now I have the lag data, difference 1, difference 2, based on 12 months, and then after the 12 months, we difference it once. So I have the difference data now. After that, I'm going to split the data into training and split. So split or partition, let's say partition the data set. So the training will be containing, we can use filter index from the lag data. So I'm going to go to lag data and use filter index. So the filter index will contain everything from 1992 February up to 2001 March. Also, we're going to have the validation set. The validation set is going to be, again, the same thing from the lag data. Then we're going to change the date from April here, from April 2001 April, up to end of the data. So this is the training. This is the validation set. Now, after the splitting, we will be fitting the ETS. Fit ETS. We will be fitting SES using ETS. Simple exponential smoothing using the function ETS on the twice differenced data. So I'm going to call it fit.ets. On the training data, I'm going to pass the training data to a function called model. And the model, we're going to have ETS equals, the function is ETS capital letter. Now, what is my response variable? The response is the difference, 12, 1. Then we are going to conduct the ETS, and we are going to have additive error and no trend, no seasonal. So it's going to be ANN. So the error is going to be A, additive error, plus the trend is going to be no trend, because we are building this ES on detrend or deseasonized and untrended data. Also, I'm going to have non-seasonal. So season is going to be also no. I'm going to do something. If you remember the formula that we have an alpha, the parameter, I'm going to pass my alpha. Then we tune the alpha. We change it to get the best thing, to get the best model. So I'm going to call alpha. So I'm going to pass alpha to the trend argument. And this is the way that is going to work. So this is the first model I'm going to make. After that, what I'm going to do, this is enter. I'm going to add another model, which is the optimized model. I'm going to ask R that, hey, R, optimize the value of alpha and give me the best ETS model, the best ANN model. So I'm going to call it ets.optimize, optimize, okay? Then I'm going to say ETS. I'm going just to copy the same thing. I'm just copy the same guy. But I'm going to remove alpha. I'm not going to fix alpha. I'm going to ask R to find the very best ETS here, the best value. So let's run this. We got an error. Oh, this is trend. So I got the fit ETS data, and we can look at the difference between both guys. So library, I need a broom, and we will look at the tidy of the fit ETS. I can look at the report. Let me check the report. So let me look at broom, tidy. So tidy gives you the values of alpha. So look at the values of alpha, both values of alphas. So we have different values for alphas, and we have different values for the first alpha is about negative or 0.02. This is about 0.0001. We look at the report. So the ETS, if you look at the report, that we have smaller values for the optimized. So we're looking for the MSE, AIC, AICC, all of these. If you look at them, they're generally speaking less than less errors. So less error, okay? So you have less error in terms of this sigma squared. So these are less error for the optimized model. So that's why optimized, the automated one that has been done by the machine itself. So give better, probably better uh, performance on the training data. Probably this is, I mean, this is not always the best thing to do, because sometimes it's going to be the case. We will be having the case of what's so called overfitting. Okay, overfitting. So the model overfits, so it's not going to perform well on the validation or in the next on the validation or in the entire data set or on the future. So let's do forecasting now on the validation data set. So, oops, forecast for the validation. So we are going to call it forecast ETS, and we are going to take the model, which is the fit ETS, and we are going to forecast H equals number of the validation. So how many data set, how many values do we have in the validation, which is the validation horizon. And we can print this one, by the way. It's a print. So these are the values, negative 6.3, so one value across the entire thing, across the entire validation. We can look at actually for the fitted values for both. So let's look at fitted values for both models. I'm talking about the optimized model as well. So let's look at the fitted values for the fit ETS, because remember, for fit ETS we have two values. Here, by the way, if you look at, we have mean, we have difference, we have the difference, we have the other mean. So we have the other mean. We have two means here. The first one for this is for the optimized. This is for the normal, the one that we have alpha, fixed alpha for. So to look at the fitted values, these are the fitted values for both of them. I will make it bigger. So you will see the fitted value for both models. This is for the ETS. And so this applied, these are the values on the data set. Look at the values. And remember, this ETS, this is optimized. So look at them, very close to each other. It's kind of overfitting. Again, we are fitting over what? Remember, the response variable in this case is the twice difference values. So we have a twice difference number there. Let me go to the lag data. This is our response variable, because this is our deseasonized and the one that has no trend, no seasonal, right? So let me go back here. Let's just graph this. Let's graph this, and let's plot the whole idea. Plot the whole thing. So we are going to do the auto plot. let's let's do auto plot. Auto plot for the level equals null. So let's plot this. So this gives you the difference values on the forecast or the yes, the forecasted values on the validation set. This for the ETS, this is for, but I mean, this doesn't make any sense to see it like that. So let's add geom line. Let's add the lag 12.1. I mean, let's the twice difference value. Let's add the like the original response one, right? So let's add geom line. Aesthetic is going to be, I'm going to map y is going to be the difference 12, difference 12.1. This is my y. And the data, I'm going to take the data from the lag data because this exists in lag data, right? Let's look at this now. This makes a lot of sense now. We have the difference. This is the the y-axis, which contains the difference, the level value, the level time series. The ridership when we remove the seasonal and we remove the trend, we got this guy, and this is the performance on the validation set. I can just we can add let's add I mean just the whole forecasted value. So let's add the whole fitted. So let's add another geom line. Okay. Aesthetic, let's add the fitted. So dot fitted y equals dot fitted. And I'm going to take the data from the fit yet, yes. So the data is going to be the fitted value from the model that we have built. So we can change the color just to make it the color. Let's use red. By the way, we can make it more transparent. So alpha, we use this is alpha is different than the alpha that we talked about. This is alpha. Let's make it zero point 0.5. Yes. So look at the performance of the fitted values. So this graph is the forecasted or the fitted values calculated by the model on all of the data sets. On all of the data sets. But we have an issue now. The issue is it just shows one of them. We don't see both of them. We do not see the ETS for the optimized, the ETS for the, it's not clear. So what we have to do, we have to add another level, which is the, let's face it, trap. So let's separate them. I'm going to separate this by the model. So number of columns equals 1. I'm going just to keep I'm going to keep them in one column underneath each other. Face a trap. Face a trap, I have tilde dot the model. That means the models, we will be dividing this based on the models because we have two models, ETS and ETS optimized. I'm going to get two graphs underneath each other. This is what I'm expecting at least. And this is correct. What we got is what we have expected. And this is for the ETS. This is for the ETS optimized. This is not a straight line, by the way. We've seen the numbers 1.4467, 1.4489. So it's kind of overfitting. It gives you, so that's why these are looks like straight line, which is not the case in this case for the training data. This for our alpha, this is the way that we have chosen alpha 0.2. As we said in the lecture, the best value has to be between 0.1 and 0.2 to avoid overfitting. And this is the case. We don't want to have an overfitting as what's happening here. So this is the ETS. In the next recording, I'm going to perform. By the way, we can check the accuracy. We did already the accuracy on the whole entire thing. So let's check the accuracy first, then we move. Accuracy. So let's call it accuracy on the validation. Accuracy. Fit ETS on the validation. It's forecasted, not fit. Forecasted dot ETS. This is the forecasted. Let's look at the accuracy, by the way, on the, what's it called? The testing values. Let's put them together. Let's row bind. Row bind. Let me call this A and B. So the training and validation or testing. This for the training, this for the validation or testing values. So this obviously looks, both, okay, both models did better for the testing values, which is good because we are getting less values, smaller values. Yeah, but we are expecting. I mean, we are hoping that the model does well for the validation sets or testing sets compared to any other sets. But anyway, so this is just an example about SES and finding the accuracy. And let's just expand on this. And because there is no need to do differencing and detrending. I mean, we should think about more sophisticated method, which is in this case, because if you remember in this data set, we have seasonality and we have a trend. So we are going to think about hold winter, right? Hold winter. So let me do it just right now instead of starting a new video. So let's use hold winter here. Hold. Remember that we are doing hold winter. Why? Why is that? Because hold winter when you have seasonality and when you have a trend you do hold winter. So I'm going just to do all of them in one code chunk. So let's call it fit ets hold winter. Okay, and we are going to do this in the training data. So we're going to build the model in the training data. The model is going to be ets again equals. Now I'm not this is the point. In the whole winter, I'm not going to build my response variable is going to be the ridership, not the difference, not the twice difference data, because whole winter deals with data that has seasonality and trend. So I'm going to do ridership here, ridership tilde, then my error. Now we are going to decide, is it additive or multiplicative? Now the error, if you look at this, let's assume that the error is like it's not constant. It's not additive. So let's use multiplicative error. Also the trend we said before no. Now we are going to say it's additive. We do have a trend and let's assume that it's additive trend plus the seasonal. We do have seasonal and it looks additive to us. Also, it's not something that expanding, it's not a multiple every time. It's not multiple of things, of numbers. So we did multiplicative error and additive trend and additive seasonal. After that, we can just run this guy. So let's look at the report and we should see these values. Now, the question is, how does this do compared to other models? We can just compare them, but let's first do the forecasting. So let's do the forecasting on the validation set, okay? So forecasted ets.hold. So I'm going to take ft ets, the fit ets.hold. I mean, I'm taking the model. I'm going to apply this model on the number of row of the validation. I mean, the same steps we did before. And we can just print this if we like. So these are the mean. Look at these are the riderships. So these are the riderships. Let's look at the fitted values. These are the forecasted, I mean. So let's look at the fitted values and let's just combine them, put them together. So let's look at check the fitted values of the model, which is the fit dot. So these are the fitted values. Now we can just compare these values, by the way, with the ridership. So, I mean, this is the performance of the model on the validation set, right? The training set, sorry, on the training set. So we can put these together next to the ridership and see how they look like, but we can actually graph them. So let's just graph them and see how it goes. Let's just plot. So I'm going to do auto plot. I'm going to plot again the forecasted halt winter. Level is going to be null. So if you just auto plot this, we are going to see this on the validation set. So it doesn't make any sense to see this alone. So we have to add another graph, which is the geom line on the rider. I mean the whole entire geom line on the ridership. So aesthetic y equals ridership because we're giving ridership. And the data, we're going to just look at Amtrak data, amtrak.ts. We can make another color just to make it black. Let's do that. So now it makes sense. Now we have the ridership data. the entire data set, the original one, and we have the forecasted one. The forecasted one. What I did here, by the way. Yes. So this is the forecasted data set, the forecasted values, sorry, on the validation set. This is my validation. Look how does this do compared to the simple exponential smoothing. The simple exponential smoothing was a straight line, just horizontal line, just one value for the whole thing. Now we have a very close fit compared to the SES. So whole twinter, because we're working with the whole data set, so it makes sense to us to see the actual values for this. It doesn't seem to be easily to be interpreted because we're working on the twice difference values. Also, remember that when we do twice different data set, we are not getting a clean level. We still have noise. We still have noise there. Here we have noise, but here at least you can see how does this do. Also, you can look at the fitted value on the training. So let's add the fitted geom line as we did before. Aesthetic, y equals dot fitted. But let's take the data from fit. I have to take augment, I guess, but let me try. Let me take the color to be red. Yep, I think I have to do augment. Let me check this. So now we're looking at what? We're looking for the fitted value on the training. So this is how the model does on the training data. So how close is the model compared to the actual data? So these are the fitted value. So these are in the red, the fitted value, in the blue, the forecasted value. Look, the difference between the red and the red, the model has seen the values, but the blue, the model has never seen the values. So we apply the model on the new set of values. So this is the difference between both of them. So this is whole twinter, and you can play with this. You can change from and see really compared to the report and accuracy if you're getting something else or better than this. This is the whole thing. Thank you.